Dear students, now that we have understanding of S-curves and use of unit hydrographs to determine the flood hydrographs for any depth of storm and combining S-curves or method of interpolation, we can also obtain the unit hydrographs for any duration. It is time to move to our next topic on synthetic unit hydrograph. Now there is one warning that I really want to give at beginning of this lecture is that lot of equations are involved and that too empirical equations. While I would not expect my students to cram those equations or learn those equations by heart, but at least you should understand that what is the use of synthetic hydrograph, unit hydrographs, how to use those equations to obtain a unit hydrograph for basins where obtaining the unit hydrographs from real data is difficult. So as I said, these hydrographs are empirical in nature. That is, scientists they try to understand multiple hydrographs and as a result of which consequently the unit hydrographs obtained for a particular watershed and try to develop the relationships which are empirical or totally governed by data. Second thing is that these are typically used in those watersheds which are hard to access. For example, if you talk about the rivers, many of these rivers they flow through wilderness and establishing gauges on rivers is sometimes costly and sometimes it is infeasible. But we still want to have a good grasp on response of such watersheds to different kind of storms, because even there we may have life, we may have biodiversity, and we want to understand that if precipitation happens, how that is going to propagate through watershed. And since they are developed empirically, they are applicable to specific regions only. That is, if I have developed these hydrographs for one basin, either they would be applicable only to that basin, or we will define a concept of meteorologically or hydrologically similar basins. So these basins they have to be twins or siblings if we have to apply the hydrographs developed as part of synthetic unit hydrograph theory. So the scientist who popularized this concept of synthetic unit hydrograph was Snyder. So that's why they are popularly known as Snyder's synthetic unit hydrograph. The word synthetic means that it is derived from data or from empirical calculations. And if we look at from competitive exams perspective, some questions may be asked, but again, as I said, we will try to grasp the key concepts involved in the Snyder's synthetic unit hydrograph. So, if we have to develop a synthetic unit hydrograph for any watershed, what we need? We basically need on x-axis time, which should be in hours. So we will have time here in hours, and on y-axis we will have discharge, typically in meter cube per second. Since we are talking about a unit hydrograph, we will have the depth of precipitation as 1 centimeter. Since we are talking about this in Indian context, this would be in centimeter. In US, this unit hydrograph would be defined in terms of inches normally. There would be some duration associated, that this is happening for some duration of rainfall, and this is the duration of effective rainfall. And then we want to know that what is the width of base, and we will call it as TB. So the time, because it's in unit of time, so it is going to be TB. We need to understand what is the magnitude of peak and when it occurs. So what we would do, we will measure the peak of hydrograph from centroid of the precipitation box. So if this is happening for the duration of TR, this this we will take an offset of TR by 2 because this is a uniformly distributed precipitation event, and from this to peak we will say that this is TP, which also represents the lag time. The physical interpretation of lag time is it represents that once precipitation happens, how much time the farthest drop of water would take to reach the point where we are measuring the discharge, and which is typically mouth of the watershed. So we also know that in addition to where it is occurring, what is the magnitude of peak? So we need to know what is QP. Also, if I give you certain points, that means if I tell you that what is the width of this hydrograph at two sections, then what we have is that using all these points, we can try to join the origin with these points using some smooth curves and making sure that it ends at TB. We can come up with an approximate shape of hydrograph. Generally, if we have data corresponding to these points, we end up with developing the realistic hydrographs. If we are just developing it with help of equations, we end up with synthetic hydrographs. Now, since the total depth of precipitation under consideration is 1 centimeter, they again become synthetic unit hydrographs. So, after studying large number of watersheds into the Appalachians highland in United States, Snyder developed some series of equations which we are going to learn in these sections. So he said that we can obtain synthetic hydrographs by knowing two constants or parameters. And we say that these parameters are CT and CP, where CT is a regional constant that accounts for the slope and storage effects. CP accounts for the retention and detention effect. And this will become very clear as we move forward into our discussions. In addition to these two parameters of CP and CT, let us consider a watershed which is going to have some stream networks. So there are two lengths on which the time of flow would depend. For example, what is the distance between farthest point in the watershed along the channel? So for example, this is the longest channel that we have. So we take this stream which has the highest order and or the highest length, and we measure the straight distance between the point where our gauge is there, where we are making this hydrograph, and the length of the farthest point. Similarly, we take centroid of this watershed, project it along the longest channel, and measure LC. So LC represents the centroidal length, and L of course represents the distance of the farthest point along the straight line. So Snyder said that for a standard duration of precipitation event, we need to know TP, we need to know TR, because as I said that we are developing this unit hydrograph for a particular duration, which in this case is TR. And if we know TR, we can derive the hydrograph or synthetic hydrograph for any other duration using some of the standard relationships that were proposed in Snyder's synthetic unit hydrograph theory. So he said that TP is equal to CT into L times LC raised to power 0.3. Again, this is coming from empirical observations made on large number of watersheds into a area of interest, but these relationships are also applied outside that area, and we will solve some examples, and that would become clear that how we can do that. So there TP becomes CT equal to LLC 0.3. So if we know CT, L and LC, we can determine that what is the lag time here. Now, once we determine the lag time, the second relationship that was proposed is that TR, or the standard duration of rainfall, that is effective rainfall for which we are drawing this synthetic unit hydrograph, is TP divided by 5.5, and this is also in hours and this is also in hours. Now we have determined TP, we have determined TR. We need to know the magnitude of Q to identify our first point. So further it was proposed that if we have to measure QP, we learned that it is essentially given by the area of watershed into 2.78 if we are accounting for units in meter cube per second, because everything is in hours and we are taking this to meter cube per second, divided by average intensity of precipitation that is happening. Now, since 1 centimeter of precipitation is happening over the duration of TP, we can simply say that QP is equal to 1 by TP into A into 2.78, which is the correction or the conversion going from hours to seconds. And this assumes that whatever is falling into that watershed is contributing towards runoff. But we know that there would be some depression storages, there would be some retention, there would be some detention, that means temporary or long-term storages within watershed. So we multiply it by the correction factor, which is CP, which accounts for retention and detention effect. So now if we again go back, we have determined that where our dot should be located, what is its magnitude. We have to determine now TB and two widths at any two locations. So this is the width at Q50. That means that what is the value of discharge, or what is the width of this base when we are at half of the peak flow, and then what is the width of this time base when we are at 75% of the peak flow. So now let us move to that discussion, that how we would do that. Now it was proposed that TB, that is base time, can be calculated as 72 plus 3 times TP hours. Again, this is empirical, but it tells us that if you know TP and you can calculate QP in terms of TP, and you can also calculate the base width of the hydrograph, which is somewhere here, TB, in terms of the TP, and base is the width of base is directly related to the lag time that we are observing in particular watershed. Now, another quest that remained is that W50 and W75, that is width of hydrographs at these two flows. And again, it was said that this is 5.87 Q raised to power 1.08, where Q is the discharge or peak discharge that we just calculated using formula 2.78 into area into correction factor divided by TP, and this is divided by area of catchment in kilometer square. Similarly, W75 has to be lesser than W50 because as we go towards the peak, the hydrographs get narrower. So it is said that W50 divided by 1.7 hours give us the two widths that we are looking for. Now here, one thing that we have to look carefully is that all these formulas, they are proposed for the standard duration of precipitation, and if and we say that that is TR, which we have already calculated in terms of TP as TP divided by 5.5 hours. So we have everything to determine that how a synthetic unit hydrograph for TR is going to look like. But in a real world, the duration of effective rainfall that we are going to observe may vary, and TR may be different from the T small r, for which we have developed our OR relationships. So Snyder again studied that how we can convert the lag time for any duration of effective rainfall, and the relationship between TP dash and TP is given by 21 upon 22 TP plus TR divided by 4, where capital R represents the non-standard duration of effective rainfall, and TP is what we have calculated using the standard formulae. Now, using all these equations, we can determine without even going to the site that how our hydrograph is going to look like. Now, the question arises that can we apply it the hydrographs that we obtain here or the parameters that we obtain here to any other hydrological basin or a similar catchment? So, to cover that, the concept of meteorologically similar catchment was proposed. For example, in India, if we talk about river Ganges and river Yamuna, so when both of them flow through upper Himalayas, they encounter very similar kind of terrains. So hypothetically, we can say that we can use the same parameters CP and CT for both these catchments, and whatever unit hydrograph we learn for river Ganges, we can apply it to river Yamuna in upper reaches and vice versa. And so if we know the nature of synthetic unit hydrograph for one of the rivers, we can estimate that how the unit hydrograph for another river is going to look like. To understand this entire theory, let us try to look into one example which we again borrow from our textbook. So here the question is that there are two catchments, A and B. A could be Ganges, B could be Yamuna, and they are considered meteorologically similar. So the catchment properties are shown below. That for catchment A, we know that length of the farthest point along the channel as 30 kilometer. Length of centroid from mouth of river is given as 15 kilometer. Area of that catchment is 250 square kilometer. For catchment B, we know L, LC, and area is 400 square kilometer. Now it is asked that for a catchment A, for we have a 2-hour unit hydrograph, and it is found that it has a peak discharge of 50 meter cube per second. The time to peak from beginning of rainfall excess was 9 hours, and using the synthetic unit hydrograph method, we have to develop unit hydrograph for catchment B. So see that all the information is given for catchment A, and we want to derive the synthetic unit hydrograph for standard duration for catchment B. So let us see that how we will approach this question. So first of all, we will focus on what is given. If you note that it is already given to us that a 2-hour unit hydrograph was derived. So we are given the TP dash or sorry TR, not TP dash, TR, T capital R specifically, where R happens to be non-standard duration of precipitation, because it does not account for the watershed characteristics. So we say that it is given as 2 hours. Also, first of all, what we will do, we will try to calculate the TP dash. Wherever we are dealing with non-standard units, we will use a dash to distinguish it from the standard measurements proposed by Snyder. Now, if you recall that TP dash is distance from the centroid of that precipitation. So if this event is for 2 hours, the distance TP dash would be from centroid, and this is given out, and the total distance from origin is given out to be 9 hours. So that means if this duration is 2 hours, we are left with 8 hours here, because this would be 1 hour from the centroid to the origin. So the TP dash in this case is known to us as 9 minus 1 equal to 8 hours. Now, if TP dash is known, we can calculate the standard duration of effective rainfall for which Snyder's unit hydrograph theory would apply. And we learned empirically that TP dash is 21 by 22 TP plus T capital R by 4. So TP dash is known to us as 8. This is equal to 21 upon 22 TP. T capital R is known as 2 divided by 4, which implies that TP comes out to be 7.857 hours. So we have our first calculation ready with us to develop a synthetic unit hydrograph. Now, if this TP is known, we are ultimately trying to estimate the hydrographs or synthetic unit hydrograph for catchment B. And to do that, we need two parameters, which is CT and CP, as we discussed, where CP accounts for the retention and detention and CT accounts for the basin characteristics. And we will use the equations for catchment A, apply to its sibling catchment and solve the problem. Now that since we know that TP is equal to CT into L into LCA 0.3, we determined TP as 7.857 equal to CT into L is given 30, LCA is given 15, and we raise it to 0.3, which gives us CT as 1.257. So we have obtained the first parameter that we can apply to catchment B. Also, it is known to us that QP dash is equal to 50 meter cube per second for the duration of precipitation, TP dash equal to 8 hours. And we just learned that our QP dash can be written as 2.78 into A multiplied by CP divided by TP dash, or QP is equal to 2.78 into A into CP divided by TP, where these are non-standard and standard representations respectively. Now for catchment A, we know that QP dash is 50, TP dash we already know that is 8, that is the distance between centroid and the peak of hydrograph. Area is known as 400, only unknown is CP. So here our CP comes out to be 0.576. So from basin A, we have determined both the coefficients that will help us determine the shape of unit hydrograph for basin B. So now what we will do, we will move to catchment B and try to apply all the same equations and obtain our answers here. So for catchment B, we can calculate TP as CT into L into LCA raised to power 0.3. We have already calculated this CT as 1.257. Length of catchment B is known to us as 45, and distance of centroid from mouth of river is known as 45. So this will become 45 into 25 raised to power 0.3, which comes out to be 10.34 hours. Now we have calculated TP. We know from Snyder's unit hydrograph theory that TR is equal to TP divided by 5.5, which happens to be 10.34 divided by 5.5 equal to 1.88 hours. Now that we have determined TP, TR, we can determine QP as 2.78 into CP, which we will use from the previous basin coefficient given as 0.576 multiplied by area of catchment B divided by TP, which in this case is 10.34 hours, and this comes out to be approximately 62 meter cube per second. Now we know that where this QP is happening because we know it's X and Y in some sense. This is the Y coordinate and this is the X coordinate. Another thing that we have to determine here is width at the Q at the 50th percentage of peak flow. So this width again is given by Snyder as 5.87 Q divided by A raised to power 1.08, and this approximately comes out to be 44 hours, and 75th width comes out to be 25 hours by dividing this by factor of 1.75. Now if we put all these equations into context, what we can do is we again plot our x-axis and y-axis, where this represents Q meter cube per second, and we know that if this happens to be our TR, this is 1.88 hours. From its centroid, which happens to be somewhere around 0.96, we go at the distance of 10.34 hours and put a dot here, and the distance from base is going to be 62 meter cube per second, as that is the value of our peak. So we mark this dot at the coordinate of 10.34 plus 0.96 comma 62 meter cube per second. We also can calculate TB. We learned that the relationship between TP and TB as 72 plus 3 times TP hours, and this comes out to be around 108 hours in this case. So we know that this width as 108 hours. Now, if we know Q, we also know Q50, we also know Q75, and we calculated that width of this hydrograph, assuming symmetry around the peak, is going to be 44 hours. So we will mark 44 here, 22 on either side. And at Q75, we know that this depth is 25. So we'll mark 12.5 and 12.5 on either side. Now we have obtained around 6 points, and we will join them using the smooth curve, and we have obtained the ordinates of a unit hydrograph, and this is unit, that means this is 1 centimeter, a synthetically generated unit hydrograph for another watershed without even going there, and using the data set from one of the watersheds which was accessible. Again, as I said, there are a lot of equations, but one interesting thing that is going on here is that how scientists have assimilated and used data sets in hydrology powerfully to solve these large scale problems that shape the understanding of hydrological sciences of today. With this, we will discuss the last concept of topic of hydrographs called as instantaneous unit hydrographs in our next lecture. Thank you.